Pleased to meet you too. All right. I'll begin with my opening and. Begin with my opening and. We are here for International STEM and Innovation Colloquia Series 20. Thank you to Drs. Nazir Halif and Sharifah Nur Faiza. Thank you to UNIMAP Vice Chancellor Professor Zaliman Sauli and Deputy Vice Chancellor of Research and Innovation Professor Rizal Fandi and their respective officers, as well as here for International STEM and Innovation Colloquia Series 20. Thank you to Drs. Nazir Halif and Sharifah Nur Faiza for hosting this event, as well as IEEE Sensor and Nanotechnology Vice Chancellor Professor for collaborating in this Deputy Vice Chancellor of Research and Innovation Professor Rizal Fandi and their respective officers, as well as here for International STEM and as normal, I would like to introduce everyone to our esteemed speaker for this Series 20 in this event, as well as wish you a very good evening, Dr. Stephen. Dr. Stephen Wolfram is the creator of Mathematica, and Prabha, the moderator for this ISICS mathematical software, Wolfram Alpha and the Wolfram language, as well as the author of a new kind of science. Besides being the founder and CEO of Wolfram Research. Good evening. For nearly 4 decades, he has been a pioneer in computational thinking, into significant discoveries and innovations across science, technology, and Wolfram Alpha. And born in London in 1959, Wolfram was educated in Oxford and Caltech. Being the founder, published his first scientific paper at the age of 14, and had received his PhD in theoretical physics from Caltech by the age of 20. Discoveries and innovations. Early work in high energy physics and cosmology included several. Born in London in 1969, starting with computers in 1963, Wolfram developed the first scientific paper at the age of 15, which was released commercially in 1981. Recognized with the MacArthur Fellowship in 1981 for his work in physics and computing, Wolfram then focused on complexity in experiments with cellular automata. Starting with computers, this led to significant discoveries in the first his work introduced concepts like computational irreducibility, recognized in the fields such as complexity theory and artificial life. In 1986, Wolfram founded the journal Complexity, and that's his successful academic career preceded the launch of Wolfram Research. Development of Mathematica began in late 1986, with its first version released in 1988. Mathematica's success established Wolfram Research as a leader in the software industry. By 1991, Wolfram balanced his successful academic career preceded the launch research, leading to new discoveries. Development of mathematical framework began in late 1986. Book, A New Kind of Science, published in 2002, was acclaimed for its paradigm shift research as a leader in the software industry. Wolfram Alpha, in 2009, revolutionized computation and AI, becoming widely used for computing answers and empowering intelligent assistants. In 2014, Wolfram introduced the Wolfram language, a knowledge-based language integrating vast computational knowledge and enabling more sophisticated and accessible programming. Wolfram's educational contributions include founding the Wolfram Summer School in 2000, publishing an elementary introduction to the Wolfram language, introduced the Wolfram language, 2016 book Idea Makers, offers personal insights into influential figures and their ideas. As president and CEO of Wolfram Research, include the Wolfram Summer School in shaping business technology and future directions. To the Wolfram language. This morning, for us, Dr. Wolfram will talk about Idea Makers, Computation. There will be a Q&A session at the end of his talk. And before I pass president floor to Wolfram Research, the Wolfram Wolfram, I would like to ask one simple question, which was earlier, Mathematica or MATLAB? Will talk about Idea Makers, Computation. There will be a Q&A session at the end of his talk. And before I pass president floor to Wolfram Research, the Wolfram, I would like to ask one introduction, which was earlier Mathematica or MATLAB. Will talk about idea makers with computation. First, there will be a Q&A session at the end of his talk. And before I pass the floor to Wolfram Research, Wolfram, I would like to ask one simple question, which was earlier Mathematica or MATLAB. Will talk about idea makers with computation. First, there will be a Q&A session at the end of his talk. And before I pass the floor to Wolfram Research, yes, I do agree. There seems to be some interfering audio. I'm sorry for it, Dr. Just give us a few minutes. Somebody's mic is on. Please mute yourselves. Yes, I do agree. There seems to be some interfering audio. I'm sorry for it, Dr. Just give us a few minutes. Somebody's mic is on. Please mute yourselves. Yes, I do agree. There seems to be some interfering audio. I'm sorry for it, Dr. Just give us a few minutes. Somebody's mic is on. Please mute yourselves. Yes, I do agree. There seems to be some interfering audio. I'm sorry for it, Dr. Just give us a few minutes. Somebody's mic is on. Please mute yourselves. Yes, I do agree. There seems to be some interfering.
I mean, back in very ancient times, one could imagine that human language had not yet been invented, and people were like pointing at different rocks and indicating each rock separately. And then the idea of human language and the idea that you could just have a word that represents a rock, any rock, came into existence. So sort of the first big level of formalization was the invention of human language. I mean, back in very ancient times, one could imagine. Oops, I think we have human language had not yet been invented, and people were like pointing at different rocks and indicating each rock separately. And then the idea of human language and the idea that you could just have a word that represents a rock, any rock, so came into existence. So sort of the first big level of formalization was the invention of human language. I mean, so then in very ancient times, one could imagine. Well, I was going to say human language had not yet the sort of, and if we look at the sort of progression of formalization, the next big step was the invention of logic, and then the idea that you could take things that you said and abstract from them this sort of formal layer of pure logic. Then there's mathematics. That got really underneath. Wolfram Alpha is taking whatever you type in natural language. If I say something like, what was the population of Malaysia in underneath 19... Wolfram Alpha is taking whatever you type in natural language. If I say something like, what was the population of Malaysia it's taking underneath natural language. Wolfram Alpha is taking whatever you type in natural language into the precise computational language. What was the population? So let me now switch to showing you Wolfram language directly. It's taking underneath natural language. What we can do, we can start translating it to some computational language. What some trivial computation here? So let me now switch to showing you Wolfram language. It's taking underneath. So make a geolist plot of those cities. And there they are. And now we could say, for example, let's take those cities and let's make a, let's say, find shortest tour. So this is going to give us a, is going to work out kind of the combinatorial optimization of working out that sequence of cities. And it says there's a path that's about 6,000-mile path that allows us to visit all of them. Let's say we do this. Let's take those cities and let's use this list of this ordering here. And let's say we take the cities and we use that list of that. And there they are. And now we could say that ordering there. and then we say geo list plot, and then let's join these points up. This is going to give us, and this should show us kind of a tour that we could take among those cities that takes the least distance to get between those cities. So that's kind of an example of again, of being able to take, in this case, cities and compute with them. And this is kind of the big theme, is to make everything in the world computable. So, for example, I don't know, we could pick another example. We could pick a chemical. Let's say we have something like let's pick a molecule. Let's say decane. That's a chemical, and let's say now we have that be we say that we want a molecule of that form as a molecule, and now let's say we make a 3D molecule 3D plot of that molecule, then we'll get this is not a very exciting molecule, but we can let's pick a better example. Let's make a biosequence. Let's make something where we take a series of base pairs, and that's a biosequence that will be a DNA sequence. Now we want to say biosequence translate. I think that will translate that DNA sequence into a peptide sequence that has to be in groups of 3 in order to make it a protein. Now we can say biomolecule plot 3D of that thing. Now, hopefully, I don't know what it will do for this random protein. It will try, there we go, wasn't very exciting in this particular case, to figure out how that protein would fold up, a protein with that particular sequence, how it would fold up. For example, we could take that biosequence there, and we could say just molecule plot 3D, and it will probably be able to, I don't know quite, there we go. So now it will show the individual atoms in that particular biosequence. So we can compute about all kinds of things. And this is sort of the big idea here, is to be able to take the things that we care about in the world and compute with them. So, for example, we might take, I don't know, we could take something like movies. We could say, let's pick out 20 random movies. So there'll be a bunch of movies. I don't know what and we could say, let's get the movie posters for these 20 random movies. And it may not have all of them. Okay, so many of them are missing here. We have some of those movie posters. Let's delete the ones that are missing. There we have a list of movie posters. And for example, we could say, make a feature space plot, use machine learning to arrange those movie posters in a way so that, well, it's not very exciting in this case, so that similar movie posters appear together. We could do that, or we could take those movie posters and we could say, make a plot of the colors that appear in those movie posters. So that would be line 33 there. Okay, so that's showing which colors appear in those movie posters. So it's remarkable what one can compute about in the world. I mean, you could compute, I don't know, what could we do? We could say something like the distance between, let's say, Mars and Jupiter planets right now. And we can compute the distance between them, and it gives us the result. We could do that as a function of time and so on. We can compute all sorts of things that way. So let me show you the thing that actually we just released today, which is a notebook assistant that allows you to, just in natural language, ask questions here. So let's say we say, make a picture with images of planets proportional to their mass. Now, what it should do here is to actually generate Wolfram language code. Let's see what it does. It's always a bit unpredictable when you're using AI systems like this. Might have to, it's because this is probably the first time I've done this on this computer. It may have to load up some things to make it work here. Come on.
The language seems very mathematical-ish, is it?
Still thinking. Let's see what it does. So we asked it. We just used natural language to ask it this. Let's see, and okay. So it's trying to do that computation. Let's see what it manages to do. I think I should have asked it to just show me the code it's producing. Okay. Okay, well, it managed to do it, but let's just say, show me code, and hopefully it will be able to do that here. And let's see what it does. So we asked it. Just use natural language to ask it. There we go. So now it's produced the Wolfram language code for doing this, and I could just run that here, and I'll get that result. I could say something like arrange that in a grid or in a collage. Okay. Well, it managed to see whether it does it differently here. But you see the result. So I consider it very remarkable that it's possible to go from pure natural language to something that is precise like this, and that can be, okay, let's see what this does. Let's just run that, see whether it produces a different result. Okay, that's very nice. So that produces just it's a bit low resolution. I should have told it, but it produces a collage of those images. So this is something that's new that I think provides a kind of a good way for anybody to make sort of anything computational. So if I say something like, but you see the result. So I consider it very remarkable. Something about natural language to something that is precise. It's a good example here. Okay, let's see what this does. Let's just run that. See whether it produces a different result. Okay, that's so that produces just how would I it produces a collage of those images. So there's something let's say what shape find me. Let's try this. Let's try something very difficult. Find me a molecule that is in a spiral shape. Something about I have no idea how it will be able to do this. I don't know how to do this immediately, but let's see what it does and see whether it manages to come up with kind of a computational approach to that problem. Let's see. Okay. Well, that's nice, but this will give you a representation of a spiral, right? That's a good start. Okay, that's a conical spiral. That's very nice, but make a picture of that. But now I said I wanted a molecule in that shape. So how is it going to do that? It's no idea how it will be able to do this. I don't know how to do this immediately. Okay, now it's trying to generate that picture. Come up with kind of a computational and hopefully it will succeed in doing that. Let's see. Okay. Oh, here we go. That all right. So now this will give you we can run that. Now we've got a picture of a spiral. But now I was wondering whether it would actually be able to start figuring out how to make a molecule of that shape. It's a difficult thing to do, but it managed to at least get to the beginning of that. It sort of started to define how we would think about that problem computationally. It's maybe afterwards people can ask me different kinds of areas, and we can take a look at what we can do to make those areas computational. Well, so this is kind of sort of the big effort is to take sort of everything in the world and make it computational. But now the question is, what's the world really made of, and how computational ultimately is the world? And this gets us into questions about making models for things and questions about physics and so on. I'll tell you something that I started doing at the beginning of the 1980s. I was really curious about sort of how complicated things managed to get produced in the natural world. And I was certainly well aware of mathematical equations, all the things one can do with mathematical equations and so on. But I got interested in how one might generalize those to think about things that could be represented by some theoretical rule, but not necessarily a mathematical equation. And that led me to start asking, well, can we start thinking about systems in terms of just arbitrary computational rules? And so I started looking at what do simple programs in the sort of computational universe of possible programs, what do they do? And so here's a very simple example. This is just a line of cells, each black or white. This is a rule that says if you have, for example, white, white, black, you'll get a black cell on the next step. So let's see what this does if we run this rule. So we can say run that rule. We can say we can say run it for 40 steps, for example. Say show a mesh so it's easy to see what's going on. And this is the result. So we had a very simple rule, and the behavior that we get starting from just one black cell at the top here is correspondingly simple. We could change the rule. Let's say we use this rule instead. Let's run that rule. Well, then we get a more complicated pattern. We keep going for a while longer. We'll find that the pattern is very intricate, but it nevertheless has in some sense a very regular form, a very regular nested fractal form. But then the question is, well, what about other systems like this? If you just look out into the computational universe at all possible programs, what do they end up typically doing? So this is an experiment I first did in the early 1980s to just look at this computational universe of possible programs, to sort of point one's telescope out into the computational universe and see what's out there. Let me show you what happens. So these are the different possible programs, always of this form, that different arrangements of bits here, and this shows what they do. And so you see some of them produce nested patterns and so on, but then after you get to the 30th one of these, Rule 30, you get my all-time favorite science discovery. So the rule for this is very, very simple. So we can see what is Rule 30 here. We can look. There's the rule, very simple. But if we say, well, what does this rule lead to? This is what it leads to. So even though the rule is simple, the behavior that it produces is not simple. There's some regularity over on the left here, but for many practical purposes, the behavior that we get is completely random. We look at the center column of cells here. For all practical purposes, it seems random. So this is a very remarkable thing. It's sort of an intuition-breaking thing, that from even a very simple rule, it's possible to get very complicated behavior. And this is something that I think is the big secret that nature uses to make most of the complexity that we see in the natural world. Well, there are many sort of theoretical consequences of this phenomenon. One of them is a thing I call computational irreducibility. Here's how that works. Let's say we want to predict what will happen a large number of steps in the future with this particular system. If we had a different kind of system, let's say we had this system here, pretty easy to predict what will happen a large number of steps in the future. If it's a power of 2, it's a 1, otherwise it's a 0, basically. It's very predictable. And that's kind of what we're used to in traditional mathematical science, that once you've defined the rules for a system, you've got the equation for a system, you can just solve that equation and figure out what the system is going to do. You don't have to figure out where the Earth's going to be, and if it's an idealized Earth orbiting an idealized sun, you don't have to sort of trace a million orbits to find out where the Earth will be in a million years. You just have to fill a number into a formula and see the result. So that's kind of what we come to expect from kind of the exact mathematically based sciences. But when we have a system like this, that's not the story. The story here is that this is a computationally irreducible process. It's a process where the only way you can know the answer, the only way you can know what happens after, let's say, a million steps, is to run a million steps and see what happens. So this phenomenon has a lot of consequences for kind of the sort of limitations of science. What can science not predict? In a sense, it seems like sort of a bad thing that we can't figure out what's going to happen. In a sense, philosophically, it's a very good thing because it's what makes kind of the passage of time meaningful. If it wasn't for that, we could just say, well, what's going to happen in the end? The result of everything in the universe is the number 42, for example. And we could just jump ahead and not live through all those steps of time that correspond to the actual time in the universe. But in fact, computational irreducibility means that the passage of time has sort of a fundamental meaning. It's also the thing that leads to our impression of free will, even though the underlying rules may be deterministic. Computational irreducibility has many consequences. It's something which implies that there'll sort of always be surprises. As you run a system, as you compute things, you will always be surprised by what it does. And that has consequences in terms of the fact that there'll always be inventions to be made. It has consequences in terms of the fact that if you're building an AI system, for example, and you say, I want to know what the system, I always want to make sure that the system will never do the wrong thing, for example. That's something that computational irreducibility tells you you can't do if you want the system to kind of make the best use of its computational resources. If it's making the best use of its computational resources, it will be behaving in a computationally irreducible way. And so it will be able to generate surprises in what it does. Well, so this question, so we've now seen that even a very simple rule like this can produce very complicated behavior like this. Then the question that you might ask is, well, what about the whole universe? Could it be that the whole universe is actually made from a very simple rule, perhaps like this? And I thought about this for a long time, and eventually about 5 years ago, we made kind of a breakthrough in understanding how that works. And I think we can now say that we understand kind of the machine code of physics. There's lots of work to be done in going from that underlying machine code to the actual physics that we observe, but we can at least see kind of the foundations of that. So to give a sense of how this works, let me describe that. So one of the things that it starts from is the following. It has to do with what is space. So back in antiquity, people kept on arguing about, is the universe discrete or continuous? Is it made of discrete atoms, or does everything kind of flow like water? And that was an issue for a long, long, long time. Eventually, at the end of the 1800s, it became clear that, well, yes, actually matter at least is discrete. It's made of discrete atoms and molecules and so on. Fairly soon afterwards, it became clear that one could think of light as being discrete, made of photons as well. And back in those days, 100 years ago, most people thought that space would turn out to be discrete as well. But nobody could figure out how to make that work kind of at a mathematical level. Well, 100 years later, we finally can figure that out. And people have assumed that space is continuous. You just put things wherever you want. But actually, that's not really the right picture, I think. I think space should be thought of as discrete, that everything is made of kind of discrete elements, discrete atoms of space. And the only thing we know about those atoms of space is how they're related to each other. So we can think about space as made of a giant network, where we have kind of relations between atoms of space. And then we can say, well, how does that progress with time? Well, we can say, let's just imagine that every time we see a piece of the network that represents the structure of space that looks like that, we'll transform it like that. And if you keep going for a while, you build up very complicated patterns of behavior. And the whole point is that what we think is the case is that everything in our universe is just made from this giant graph, or actually hypergraph, of relations between the atoms of space. So, for example, perhaps I can show you what kind of the very beginning of the universe might look like in this kind of setup. let's see. This is starting from one graph, and it's progressively being rewritten over the course of time. We're building up a bigger and bigger and bigger sort of structure that corresponds to the structure of space and everything in space. So if we wait a really long time, then perhaps the thing that we'll see in some part of space is something like this. There are all these connections between atoms of space, and there are two big structures here which correspond to black holes with event horizons and so on. And we can try and we can run this, and we'll see kind of the way that this network is getting rewritten corresponds to, we'll see these very tiny black holes. There's kind of wiggling around a lot. There are a lot of quantum effects and so on. And eventually we'll see these two black holes merge, and we can compute kind of the wiggling of space, the gravitational waves that come out from this, and they agree with what one sees for much bigger black holes in actual experiments. So it's really a remarkable thing that if we start from just kind of these atoms of space and this network, that we reproduce things like black holes and the dynamics of those kinds of things. Here's roughly how that works. When we have a fluid, like water, made of molecules, we know the mechanics of how those water molecules collide and bounce off each other and so on. But it turns out when we look at the aggregate effect of many, many water molecules, we can derive that the aggregate behavior of a fluid would follow the Navier-Stokes equations, the standard equations of fluid flow. If we do the same kind of analysis, roughly, for this hypergraph representing the structure of space, what emerges is not the Navier-Stokes equations for fluid flow, but instead the Einstein equations for the structure of space-time. So that's kind of how those things emerge. And the point is that this network, its features represent all the things, the electrons, the photons, the black holes, and so on, that we see in the universe. And the dynamics of those things corresponds to the progressive updating of this network. Well, it turns out that not only do we get kind of classical physics and things like gravity, we also inevitably in our models get quantum mechanics. In a sense, the essential difference between classical physics and quantum physics is that in classical physics, definite things happen. You throw a ball, it follows a definite trajectory. In quantum mechanics, what one imagines is that many paths are followed, and all we get to see is the aggregate effect of many paths. And so in our models, what happens is that these networks are getting updated, but there are many different ways the network can get updated. There are many different paths of history that can be generated. And what's happening is that we are experiencing the aggregate of many paths of history. Essentially, it's the same reason that we observe a fluid to be continuous. We're not down at the level of individual molecules, seeing what each of those molecules are doing. We are, our observation of a fluid is at a higher, coarser level, where we're just seeing the aggregate effects of those molecules, and we see them as this continuous fluid. It's the same way with the structure of space, and it turns out to be the same way as with quantum mechanics. It's a little trickier because in that case, our minds are part of the system, and they are following many branches of history, just like the actual dynamics of the physical universe is following many branches of history. So quantum mechanics ends up being this story of how a branching mind perceives a branching universe. But it's rather exciting that from something as simple as these hypergraph rewriting rules and so on, we're able to derive the fundamental laws of 20th century physics. Actually, it goes even further than this, and this is sort of a much more abstract thing, but I'll mention it. Ultimately, so one big question would be, okay, why did our universe get this set of rules and not another set of rules? And the answer is, what's really happening is that the universe is running all possible rules. It's effectively taking all possible I should show you perhaps the little bit about quantum mechanics. This is kind of what it looks like to see a very simple process of we're able to derive the fundamental laws of 20th century physics. Actually, it goes even further. Let's try this. So this is now showing sort of many paths of history being produced. And we're seeing kind of relationships between the paths of history represented by those kind of pink graphs and so on. That's kind of the beginning of the story of how quantum mechanics works. But the thing that I wanted to mention is that we can also think about sort of all possible rules. This is a representation of, this is one representation of kind of the way that you can think about all possible rules being run. This in particular case, this is for Turing machines. You're essentially running all possible computations, and you're seeing how the kind of the entangled limit of all possible computations.
Recording in progress.
This is a thing we call the Roolead. And the point is that the Roolead represents everything that is computationally possible. And so when it comes to thinking about our universe, what we're imagining is that we are embedded within the Roolead. We are a part of the Roolead. And the big question is, well, how do we perceive the Roolead being part of the Roolead? And what's critical there is, well, what features do we have? It turns out that there are two critical features that we assume about us, that are features of us. One is that we are computationally bounded. When there is computationally irreducible stuff going on, we can't follow all that computation. We end up just being able to slice off some simple piece of what is going on computationally. That's one assumption. The other thing is that we believe we are persistent in time. Even though in these models, we're made of different atoms of space at every successive moment of time, it is our perception, our internal perception, that we have a single sort of thread of experience. We are persistent in time. Well, it turns out that those two features of us as observers, together with the concept of the Roolead, and the idea of this thing that represents the entangled limit of all possible computations, those things together are what you need to derive the laws of physics that we know. Actually, the three key principles of 20th century physics, relativity, quantum mechanics, and the second law of thermodynamics, statistical mechanics, all three of those turn out to be derivable from the idea of the Roolead and these features of us as observers with these particular characteristics. I think this is very exciting. It was very unexpected to me that it's possible to effectively derive the laws of physics for observers like us. If we were not observers like us, if we were very different from us, we would perceive different laws of physics. But the way we are, we perceive the laws of physics that we perceive because we are the way we are within this kind of computational structure. Well, actually, this goes even further than physics. It extends to mathematics, for example. You can say, well, what is mathematics like in the end? You could say, well, we can start thinking about sort of the kind of the infrastructure of mathematics. So we might say, well, we have some axioms that we're going to use to build up mathematics. So there's a very simple axiom, and we could say, well, what consequences does that have? Well, it says this expression is equivalent to that expression. We can keep doing that. We can say it shows that there are lots of equivalences between expressions. We say, in particular, the expression here is equivalent to this one here. We can find a path. That path is a proof that one expression is equal to another. And so we can build up kind of this meta-mathematical space, the space of all possible implications of a particular set of mathematical axioms. So, for example, we might build up something like, let's see, we might take a look at some practical system in mathematics. So let's say we look at the axioms of logic. So we can start building up here. These are oh, that's group theory. This is logic. So these are different theorems of logic, starting from axioms in green, kind of building up all possible theorems of logic. So we're looking at kind of the continuum limit, the large-scale limit of mathematics. Well, if we start building up all possible theorems of logic, most of them are ones we don't care about. There are only a few that we humans have given names to. Here are a couple. And if we keep going, we can find that sort of the the pieces of all possible theorems of logic that we find are they're few and far between. Well, we can generalize this. The whole Ruliad represents kind of the universe of all possible mathematics. And the mathematics that we do as humans is a small slice through that. And just like what we observe in the physical universe as humans with certain characteristics gives us the laws of physics, so similarly, the way that we observe the Ruliad as mathematical observers gives us the characteristics of mathematics, at least at a general level. So what are some general laws of mathematics? An example of a general law of mathematics is that it's possible to do higher level mathematics. It might be that if we're thinking about the Pythagorean theorem, that we have to kind of drill down below the Pythagorean theorem to understand kind of how we define real numbers and all sorts of details about the Pythagorean theorem. So for example, if I find it here, yeah. So this is even using a proof persistent system going down to the axioms of set theory. This is the derivation of the Pythagorean theorem. This is a representation of the structure of the lemmas in the proof of the Pythagorean theorem. It's very complicated. And it could be that whenever we do mathematics, we have to go all the way down. You know, we're really breaking things down to the point where we have, you know, we break down a plus sign into all of its constituent parts. But in fact, a big fact about doing mathematics is that we don't have to do that. It's as if at this level, we could do mathematics at the level of individual molecules, but we don't have to do that. We can do mathematics at the sort of fluid dynamics level where we're just dealing with higher level constructs. And so in a sense, the fundamental feature of mathematical observers like us is that we can sample mathematics at the level of kind of this higher level, that higher level mathematics is possible. There are lots and lots of things that can be said about the analogies between physics and mathematics and the kinds of things one can talk about. For example, one can start talking about kind of how different theorems are laid out in meta-mathematical space. One could think about different fields of mathematics as existing at different places in meta-mathematical space. One can start thinking about the correspondence between different fields of mathematics as being like the idea of moving in physical space from one place to another. So one of the things that's true about the world is that we think we can just take an object and move it somewhere and it will still be the same object. That's something we observe in physical space. That's something we can derive in our models of physics. It's not obvious it will be true because when you move an object, it's made of different atoms of space in the place where it arrives. But in mathematics, that motion is like translating from algebra to geometry to something else. And the fact that there is a correspondence between those things is something that we kind of learn from this whole computational structure. I should say when it comes to motion in the physical world, it is interesting to realize that, for example, you can understand almost mechanically how things like time dilation and relativity work. If you have an object that's just sitting in one place, it is computing its future state. It's determining what it will be at a later time. And that's what, and it's spending its sort of computational resources doing that. If you're moving the object in space, the object has to do two things. It has to recreate itself at that new place in space, and it has to do whatever internal evolution it would do. And the fact that it's having to use some of its computational effort to sort of recreate itself at a different place of space is what leads to time dilation. Because that's what means that the motion is taking up some of the computational resources, so the actual running of time for the object itself is slower, and so you get the time dilation of relativity. And indeed, when you work out the math of this, all of the actual formulas work out the way one expects in relativity. Well, let me just give another indication of sort of where this is going. I'll talk about something, well, I could talk about, let me mention two more things, and then we'll turn it over to questions and so on. Talk about some things I've been working on very recently that have to do with, well, both biology and the foundations of machine learning. So let's talk about both of those. They're both quite related. So this has to do with why is biological evolution possible and how does it work? And it's, again, we're kind of drilling down to the computational essence of biological evolution. Everybody's kind of known for 150 years that sort of natural selection has an effect and is responsible for sort of guiding the creation of organisms. But it hasn't been very clear what kind of leads to all of the different forms of organisms that we have and all these kinds of things. So this is a very simple model of that, which gets a very long way, I think, in understanding what's going on. So we can think of this as a very simple genome. So this is one of these rules. It's a cellular automaton rule, just like the one I showed you for Rule 30. Happens to have 3 colors in this case. It says what happens if we have blue, red, white here. And so start off from a red cell. This is the behavior we get. Eventually it dies out. Okay, let's imagine now that we have mutations to that genome. We make point mutations to the genome. We keep on doing that. But we try many different mutations. But we only keep a mutation that leads to a lifetime for the organism that is at least as long as what we had before. And let's keep doing that. We start off from something with lifetime just 1 step. And we keep iterating, we keep mutating, and actually we might have to mutate many, many steps. So for example, here, I filled in how many steps we had to do mutations for to get to a breakthrough where we got a fitter organism, an organism that lives longer. You can kind of see how this works. This is kind of every dot is a mutation we try. Most of them have fitnesses below what we had before, and eventually we'll get sort of these breakthroughs where the thing lives longer. Well, so that's kind of how the sort of evolution process works. Well, we can just try. This is sort of one roll of the dice for how one can do that. This is another one, different results. Another one here, different results. What's interesting here is it seems like what's happening is the system is kind of getting a certain idea, and then it's building on that idea to give higher fitness, to live longer, and so on. It's very much like what you see in the fossil record, where you see some invention made by biology that's been built on to lead to other organisms in the future. And so this idea, we can kind of study this in more detail. Many, many things to show here. But let me show as an example, this is perhaps an interesting example. This shows kind of all the ways to have a long lifetime thing with a particular very simple kind of rule. And what we see here that I think is important is that there's no kind of mechanical explanation of what's going on. Maybe in a case like this, you can say when it reaches that last part, you can kind of explain why it's going to live some number of steps. Maybe in this case here, we can explain why it's going to live that number of steps by looking at sort of the mechanism of it. When we have something like this, there's no way we can give kind of a narrative explanation of what's happening here. It's just, it happens to live that number of steps and then it dies out. This is a symptom of computational irreducibility. This is basically what we're seeing is a kind of lump of irreducible computation that biology can harness. It can find that lump of computational irreducibility that happens to lead to long lifetime or something, and then it can use that. And so the picture that's emerging of what's happening in biology is kind of the story of kind of really raw computational irreducibility. We're really seeing computational irreducibility up close because we're seeing that in what happens. We're seeing kind of, we're just seeing that the things that we see are kind of examples of computational irreducibility harnessed by biology. Now, we can look, these models are simple enough that we can just see explicitly all the possible paths of mutation, all the possible organisms that could be produced. Here's an example. This is kind of like a simple version of kind of the tree of life, where we're seeing in one branch, there's sort of one set of ideas for how to be a fit organism, in another branch, another set of ideas. So for instance, we can do that in bigger cases. This is a bigger example of that, where we're seeing sort of how long-lived organisms can be produced in this case. We can do things, we can ask questions like, well, that's an example of that sort of the path to the long-lived organisms there, the kinds of things we had to go through to get to those particular organisms. We can ask questions like, well, what happens if we kind of drive, the system, okay, here's an example where we're just asking how, if we start the system off and all the mutations are equally likely, which organisms actually survive? We're kind of seeing the fossil record play out, where for a while these were the successful organisms, and then after a bit longer, these ones started to become important, and so on. And we can start seeing what happens if, for example, we change the environment. So this is asking to evolve, to change the fitness, looking for different aspect ratios of organisms. And we see that as it changes, some organisms get to be very popular and then die out. As we change the way that the fitness that we're asking for, we'll see different profiles of what organism is successful when. So this is kind of understanding something about the foundations of biology by looking at things in a computational way. I'll just mention one thing, which is about machine learning. When we look at a neural network, for example, we see this is a typical neural network where we have an input here, an output here. We're trying to compute this function, and we've got these different weights in the neural network to compute that function. So, for example, if we feed in a particular value at the top here, it will go through the neural net, come out with a certain value at the bottom. The question is, what's really going on in the system? So it turns out you can make a much simpler version of this system in which you just have something where you have a grid of cells, and at each cell you pick one of two rules that you might apply. And you can then say, well, this is a very idealized neural network. This is a neural network that's been incredibly simplified. It's been made discrete, it's been put on a grid, but still you can make it learn things. And in this case, it's being taught to live for exactly 50 steps and then die out. Okay, and we see the same kinds of curves, fitness curves, loss curves that we saw before. But what's interesting is this is now unlike a typical neural net, where it's really hard to sort of look inside and see what it's doing. In this case, we can do that, and we can see in some cases we can kind of explain what's going on. In other cases, what's happening is kind of examples of irreducible computation. So when we ask sort of what's the big picture of what's happening in machine learning, what we realize, and we can do this for a much more elaborate, let's see if I have an example here. Well, this is a piece of a transformer network simplified to correspond to one of these discrete idealizations. I think here I was computing a sine wave here. But the point is, what one sees from this is what is going on in machine learning. What's going on is something very similar to what's going on in biology. One is, by training the system, one is picking out particular sort of lumps of irreducible computation that one can assemble to perform the task one wants. So it's kind of an interesting analogy between what's happening when one does engineering versus what's happening when one does machine learning. Let's say you're trying to build a wall. What you might do if you were doing standard engineering is to decide this is the shape of brick we want. You make lots of bricks in that shape, and then you build up the wall with a nice pattern of bricks. And it's very easy to explain how the wall was built. But an alternative is to say we're building a stone wall. We're just going to pick up rocks off the ground, and we're going to try and fit them together in such a way that in the end we build up something that serves as a wall. That's what machine learning is doing. It's also what biology is doing, but it's what machine learning is doing. It's picking up lumps of irreducible computation and assembling them to achieve the purpose we want in machine learning. And that's something, so when one thinks about it that way, one realizes that, for example, interpreting what's going on inside is going to be very difficult, potentially impossible, because really we just happen to use this lump of irreducible computation that did what we wanted. So there's kind of a big picture all of this, but just to make one last comment about kind of how this connects to things like the Ruliad. In the Ruliad, one is essentially running all possible rules. In biology, what one is doing is selecting a path through the space of possible rules to find the organisms one wants. In machine learning, one's selecting a path through the space of possible rules to build a machine learning system that one wants. There's sort of a question of what's out there in the space of all possible rules. And we can study that. It's I like to call that field ruliology. And we can study things like Rule 30, and if you go out into the computational universe, you find all these different kinds of behaviors. Those behaviors are often very non-human. It's hard for us humans to understand what's happening there. But if we use generative AI, for example, we can make kind of things out in the computational universe that are arranged to be at least close to what we can understand as humans. So, for example, here, we can say, let's say we tell a generative AI system, make a picture of a cat in a party hat. But then we say, let's look at the space of all possible pictures that can be produced as we move around kind of the computational universe away from the particular point that corresponds to that specific image. So what we see here is what I would call Cat Island. You know, there's a cat in the middle. As we go out away from the cat point, we're seeing things that are less and less cat-like, so to speak. So what we're seeing is things that for which we don't necessarily have words. When we make up in human language, I don't know, a pattern like a picture like that, we might have a word for that. We don't happen to have a word for it. And what we're seeing is that there are certain points in this space of all possibilities for which we humans have developed concepts, developed words, and so on. But there's this vast kind of interconcept space between the points that correspond to the words that we have. It's very much like what we saw in metamathematics. Between the theorems we care about, there are lots of other theorems. Between the things we care about as concepts, there's a huge interconcept space of things that we could care about, we could explore, but we haven't yet explored. And in fact, even in the simplest kind of generative AI system that I used for this picture here, the interconcept space is the vast majority of the space. The concepts that we have represent about 1 part in 10 to the 600 of the total space. And so it's kind of amazing how much sort of interconcept space there is still to explore. There's a lot to kind of explore in the computational universe, and kind of the story of exploring that is kind of the story of what's computationally possible. Computational X, fields that we already know exist, making computational versions of those is like following little paths out into the Ruliad, into the space of what's computationally possible. But the things that I think is kind of the big opportunity of these times is go out and explore this computational universe. One can explore it at a very fundamental level, kind of looking at big swaths of what's out there in the Ruliad. That's kind of this very fundamental science of Ruliology and these kinds of questions about what's underneath physics and so on. And one can also explore it at a much more practical level, looking at computational X for all X. And the idea of our computational language is to provide a kind of humanized version of computation that lets one go and, for everybody who wants to explore these kinds of things, lets one crispen up one's thoughts to put them in a computational form, to put them in a precise computational form, so that one can let the computer help one to do those explorations. And I think it's the thing that we've seen when I started introducing kind of programs as models of things back in the early 1980s. Everything was dominated by mathematical models. Over the last 30 years or so, there's been this sort of progressive transition to a point where most new models of things are computational models. And what we're seeing, this sort of foundational way of thinking about computational models that's come up in our physics project and these examples I've been showing you in biology, is kind of another major step, another major level in that process of kind of the computationalization, the way of thinking about things. All right, I should stop there, and I'm happy to take questions or comments or whatever people would like to chat about.
All right, thanks, Stephen. Can you hear me? Over the last 30 years or so. Okay. All right. I'd like to make one or two observational comments first. I noticed your English hasn't changed. It sounds very British to me, not very American.
I think to British people, it probably sounds American by this point. But yes, it's still on the British side, I think.
Okay, all right.
All right,
I noticed that when you use Wolfram Alpha, the language seems similar to Mathematica. All right, thanks, Stephen.
Well, no, what you type into Wolfram
The
Alpha.
format, yeah, the format.
I like to make, right. I mean, what you're typing in is just natural language. I mean, underneath Wolfram Alpha, it's Wolfram language and Mathematica underneath. That's what it's built with. But it's providing kind of a consumer interface where you can just come and type whatever you want to type, and it will do that.
Yeah,
That's the idea there.
and I like that when you type a high level language, it still provides you the educational form of Mathematica, what the codes or the format supposed to be. Yeah, I like that. Now, a bit more serious, on a serious note, a lot of the irreducibility and the computational things that are that you're exploring now seems predictive as opposed to empirical physics. What's your take on that?
It will do that. Well, so there's an interesting point. There are two ways you can think about doing natural science. One is you can take the phenomena as you see them and try and reverse engineer what is causing those phenomena. That's sort of one approach. Really, most major progress in theoretical science does not come from doing that. Most major progress in theoretical science, in the history of theoretical science, has come from imagining how things might work and then seeing, do they work that way, and comparing with experiment and so on. And sort of the big thing that I ended up doing in the early 80s was just saying, let's just look at this computational universe, this artificial physics, all possible artificial physics, and let's just see what's out there, and empirically observing things about this abstract universe. And that turned out to be very useful. And once you've observed things about this abstract universe, then you can say, okay, this piece of the abstract universe looks like this thing that we actually see in the real universe. And then you can start making those correspondences. But yes, it's an interesting methodological difference that a lot of what I've done builds up from the simplest foundations and then sees how those correspond to what we actually observe in nature. An exciting thing about our physics project has been this. We're starting from the most fundamental, the most basic underlying elements, then we're building up. And the question is, do we get to the same place that 20th century physics has got to? And the really exciting thing is that we do. It's not at all obvious that we would. It's not at all obvious. We might say, we build it up a bit, and then we might say, whoops, it doesn't fit this, it doesn't fit that. Let's change what we put into the model. We haven't had to do that. It's been difficult to work out the consequences of the model, but every time we've managed to work out those consequences, they agree with what existing physics says should be happening. Now, we also make predictions about other phenomena that aren't there in existing physics. So, for example, one prediction is that space is not precisely three-dimensional. In traditional physics, we just imagine space is three-dimensional, just a thing we take for granted. In our models, dimension is a dynamical parameter. So dimension can vary. There can be lump regions of space that are 3.01 dimensional or 2.99 dimensional. And that's a phenomenon that we can expect to see. We don't yet know what the best way to detect that is, but that's one of the things that's sort of a signature of this discreteness of space and the structure of our models. So so that's a place where we, first of all, we can build from very little to things that are like 20th century physics. And then we can go on and say, what new things are there that are different? Now, one important thing, when I showed you that picture of the simulation of black hole merger, for example, that's the thing that's interesting there is you can use our models as a practical way to do numerical relativity. So in other words, even though that's a way to sort of validate that the model is actually correctly corresponding to 20th century physics, is you can use the structure of the model to make what amounts to a scheme for doing numerical relativity. And you can actually do the same thing with quantum mechanics. So it's a kind of, you can, in effect, take what usually when people study something like black hole mergers, they start from the Einstein equations, which are partial differential equations, but they end up discretizing them. They usually use Mathematica to do the computations. They end up discretizing them to discrete form that's just purely fictional. It's purely for the sake of putting it on a computer. In our case, the discrete form is the real physics, and we're building up to something which looks continuous. And the fact that that works is an important piece of validation for our model. And you can actually do the same thing with quantum mechanics.
I would imagine the algorithms run on some sort of computational background there. How much would it differ? Would the results differ if the AI hardware changes?
And we're building up to something which
would the results?
Well, I mean,
would the dots be connected differently?
Is an important piece of validation. No. The thing to understand is this is an abstract model. The fact that I run it on my particular computer is irrelevant. It can be run on any computer. It will always do the same thing. It is an abstract model.
Okay.
So you can ask the question, if you were, if you use some AI system, could you make a different prediction about what would happen? The answer is no, not really. I mean, what happens is neural networks are good at broad, shallow computation. Computational irreducibility is all about deep computation. Neural networks don't do that. That's not what they're set up to do. And that's why, for example, in that notebook assistant system and in the things that have happened over the last couple of years with LLMs, with large language models, the typical pattern is people use the large language model as kind of a linguistic interface, and then they use as a tool Wolfram language or Wolfram alpha underneath to do the computational part. It's sort of a different thing. That's, I mean, the thing that to me is interesting is that the underlying kind of foundations of what's happening in machine learning have a lot of relation, it seems, to the underlying foundations of what's happening in physics. That's at a much more theoretical level. That has nothing to do with the detailed hardware on which things are implemented. And the thing to understand is when it comes to the universe is not implemented on anything. The universe just does what it does. We have an abstract representation of what the universe is doing. That's what our hypergraphs and so on correspond to. Let's see. I see a bunch of questions in the chat here.
I'm going to read that. Yeah, but I like the distinction you make between ML and AI.
Yeah. Yes.
Okay. The question there by Tasrif Surungan, with the current advancement of computation, how far we are advanced from having a supermind?
And the thing to understand is when it comes to the universe, everything I've done building computational language gives one kind of a superpower, a supermind. The things I've discovered in science by doing computer experiments, those are not accessible to a human mind. Those require a computational mind to reach them. And that's, for me, that is one of the great things that's sort of a phenomenon of the last few decades, is we can make that kind of computational supermind, and we've done that. And that's how the things that have been kind of languishing for 100 years in physics, in the foundations of biology, foundations of mathematics, and so on, we can make progress on those things because we have that computational supermind. Now, when it comes to sort of AI and the sort of traditional, what is now traditional AI, the ChatGPT things of this world and so on, there's a question of what does that look like when it gets to be more than it is. I might mention, you can find on the web, just after ChatGPT came out, I got so fed up with people asking me, how does it work, that I wrote this little book about what is ChatGPT and why does it work, what does it do and why does it work. You can find that on the web. It's actually translated into many languages now. it's kind of describing this question of what's actually going on inside. What's going on inside is interesting. There's an important piece of science that we should have discovered before, but it's showing us, and it's this. It has to do with how language is constructed. We've known that, let's say in English, sentences have the form subject, verb, object. I don't know what they are in Malay, but in English, it's subject, verb, object. We know how the parts of speech are arranged. But we can make up many sentences that have the correct parts of speech, but are completely meaningless. We have not known the semantic grammar of language. We've only known the syntactic grammar. And what ChatGPT showed us is that there is a semantic grammar of language. There is a structure to language that we could have discovered. And in fact, Aristotle, people in the 1600s, they were sort of close to discovering these things, but they kind of gave up for various reasons. ChatGPT is showing us that that exists. That's how it can construct these things that are meaningful, these sort of long sequences that are meaningful. And I think, because just to explain sort of how that works, I mean, in the end, what is ChatGPT doing? It is, I could show you some pictures. Let's see. Semantic grammar of language. We've only known syntactic grammar. And what ChatGPT, I mean, just to say something about kind of what's happening inside. So the basic thing it's doing is it's trying to figure out what's the next word in a sentence. So it's saying there's different probabilities for these different words and so on. And it's if we were saying, well, where do those probabilities come from? Well, let's say we just take English, we just look at the probabilities for different letters. We can make some prediction about, we can say these letters occur with certain probability. We can make sentences based on just those probabilities of letters. They look pretty silly. We can make sentences that are based on probabilities for pairs of letters. They look a little better. We can keep going. We can make sentences that are based on probabilities of words. Okay, that's longer sequences of letters. So by the time we're at sequences of 5 letters, we're beginning to get something that's vaguely sensible. So what was done to train ChatGPT? What was done was to show it 1 trillion tokens, 1 trillion words from the web and other places. And then its goal is to figure out sort of statistically what goes with what follows what. And in the end, so for example, if we say, I don't know, the cat sat on thee. From the web, we can see the most likely next word is mat, because there are probably 50,000 examples of that or more on the web. And that's something that we can pick up in sort of the statistics of what's there. But then the big sort of surprise is when you use a neural net to kind of make a model that extrapolates beyond what you can explicitly see on the web, the way that it does that extrapolation is similar to the way that we humans do it. And so, for example, if we are to say something like, I don't know, if we're to say that we to group digits by what looks like what, the way the neural net does this grouping is similar to the grouping that we would make. And that similarity between neural nets and what we do is probably no coincidence. It's probably a consequence of the fact that neural nets have a similar architecture to brains. But the consequence it has is it means that the sort of extrapolation the neural net does beyond the data that it knows is similar to the extrapolation we would do. But that's fundamentally what an LLM like ChatGPT is doing. It is just kind of trying to continue in a way that is typical of what it has seen before. What is remarkable is that that does as well as it does. That is, as a practical matter, something that can write essays, answer questions, and so on. The thing that has been important in recent times is kind of getting it to the point where the LLM can know what tool to use and ask a question of that tool. So, for example, our notebook assistant is a pretty complicated piece of technology that uses an LLM together with a bunch of other technology to kind of be able to compute what is a reasonable thing to generate as a piece of code and so on. Okay, so then the question is, well, what will it be like how do we generalize this? our existing, we have only a limited amount of data from what we humans have produced. And that's what we get to train neural nets on. Now, if you say, well, let's go far beyond that. What can we do beyond what humans have done? The thing is, there is much that can be done computationally beyond what we humans have done. You can go out in the computational universe, you can find, all sorts of amazing things. I mean, if we look as a piece of code example, we could look at how do we generalize this? It's trivial to go out and you find all sorts of things. You just go out in the computational universe, you find stuff like this all over the place. There's amazing richness out in the computational universe, but most of it is not richness that we have yet connected to things we're interested in doing in technology and science and so on. So in a sense, if the supermind is doing what is computationally possible, it will explore many things that we humans have not explored, but that we humans don't yet care about either. So it's a complicated thing, how we connect what is computationally possible to the things we humans care about. I mean, if we were to look, let's just take one more example here. Let's say we look at, let's do a, but most of it, let's, for example, take, and just to show you kind of, technology and science and so on. So in a sense, if the supermind, example, probably, let's say I'm going to do image identification. Let's just capture a picture of me here. I'm going to do image identification on this. This is running a neural network. We can look at what that network, okay, so it says it's a person great. We can look at that network. This is that neural net. We can go and drill down and we can see all the layers, all the kind of structure of that neural net that's doing that machine learning thing of working out what that image is of. But now we can go and look inside this neural net. We can say what happens at layer 5 or something in this neural net. What is it actually generating? Let's see what this is like. See if I can make images capture. Here we go.
We're not seeing your image.
We're seeing are you seeing the wrong thing? We can look at what that network. So it says the person great. Sorry, that was no fun. I was showing you
this one, right?
Okay, I got the right thing. Okay, let me show you that. Okay, so what I was showing you here is this is a neural net identifying that picture. This is the actual neural net itself. We can kind of drill down into all the details of the neural net. And now what I was doing here was to just say, let's look at the first 5 levels of the neural net. Let's look at what's happening inside the mind of the neural net. We see it finding all these different representations of the picture. And in some sense, these are the concepts that exist in the mind of the AI. We don't have names for most of these concepts. Its way of deciding that that was a person is quite incomprehensible to us. But so what's happening here is there is much that's going on. There's much that the AI could do, but it is things that we don't care about, so to speak. So it's a complicated thing to define what we mean by sort of a supermind, and the most immediate operational definition is what we already have through computation. And I think there's a question of what will it be like to live in a world in which computation is doing many things. That's already happening. Many things that get done in the world are done by computational processes that we don't understand. But beyond that, we're quite used to the idea that in the natural world, there are things that we can think of as computational processes going on that are things we don't understand. We just get to coexist with the natural world. We don't expect to understand how the natural world works. I mean, it's a feature of the last 100 years or so that we expect to understand how the machinery we use works. Back before that time, if you were riding a horse, you could know how to operate the horse, so to speak, but you didn't know you didn't think, how does the horse work inside? But then after the Industrial Revolution and so on, one became used to the idea of cogs and levers and so on, and being able to open up the machine and see what it was doing inside. that period of time is closing. Computational irreducibility means you won't be able to do that. Many of the things that we want to be done for us automatically are not things that you will be able to sort of look inside and see what's happening. But so I think the statement is kind of superminds already among us. The issue is, do they connect with the things that we care about? And that's more a question for us to extend the things that we care about, so to speak. How does the horse work inside?
Well, thank you. That was a very long answer to a short question.
It's a complicated question.
Yeah.
Sorry.
Yeah. All right. And I must retract my earlier statement on predictive things when I just realized most supercomputers do all this predictive stuff for weather and nuclear stuff and all that.
Are not things that right. So I see some other questions. Maybe I can pick some out of the chat here. I see some.
There's one: how to integrate computational thinking into traditional curriculum effectively.
Yes, that's an interesting question. So I think.
Thank you.
Let me say. It's a complicated question. There are many new things that one can do computationally, but almost anything that one is teaching, one can kind of show it in a more concrete form computationally. I mean, this is a story. What's really nice about computational thinking is that it's very concrete. It's not like somebody sort of tells you roughly, here's how an integral works and so on. It's like you type this in, it does something. And everybody can do that. A student can do that. A student can see what happens immediately. They don't have to wait for a professor to correct their work and say, you got that wrong. They immediately can see what's happening. The other thing that's important is that it's very easy to make discoveries with computation. It's very easy to kind of go out and just figure things out computationally that have never been figured out before. Let me show you just as an example. I just show you, we do, for 20 years, more than 20 years, we've done a summer school every year. Let me just show you, actually, I'll show you two things. I'll show you, we've done a summer school for grown-ups, and we've done a summer camp for high school students. Actually, there have been versions of this in different parts of the world as well. But I'll just show you, as an example, kind of this year's projects. These were done by high school students over a 2-week period. And it's pretty interesting to see the kinds of things that they can do computationally, so to speak. Okay, analyzing PEG solitaire boards using multi-way graphs. It's probably a whole big, long description of what happens here. But this is high school students. These are good high school students, but they're able to kind of take ideas and make them computational. And this is, okay, optimize crossword layout grids for density. Or this is lots of different kinds of things. Epidemiological modeling in urban rat populations. Okay.
Screen is not showing.
And showing the wrong thing again.
All by date showing.
Computationally, so to speak. Okay, analyzing PEG solitaire. Try again. Using multi-way graphs. It's probably a whole big long. I make the same mistake so many times. Okay, so what I'm showing you here is some projects from high school students done in a couple of weeks. So I was showing you this. Let's take this one. Explorations into infinitely bouncing cue balls in geometric shapes. Okay, or one of these ones here, simulating flocking behavior of boids within a vector field, I guess birds flying in the wind or something. And this is showing kind of the sort of computational thinking and showing what can concretely be done. And again, using the tools that we have, and this will become even easier as of today with this new notebook assistant, is it will be even easier for a student who's not really been introduced to computational thinking at all to be able to get access to these things. I will show you as an example. I wrote a book a few years ago. It's had several editions. It is kind of a introduction to Wolfram language, and this is kind of it's an introduction, or does work for high school students and sort of beyond, of kind of trying to understand the foundations of kind of how to think computationally about things. And this seems to be a pretty useful. This takes oh, I don't know, a few weeks to go through for typical students, and they get to it has auto grading mechanisms and things, so you can do exercises and such like. That's part of the story here. I will say there are many pieces to this. There's another initiative that we have. Let's see if I can pull that up. This is kind of it's an introduction. This is for high school students and sort of beyond. Kind of this is about math education specifically. This is Wolfram. I know I'm getting it on the right screen. This is approach to actually my younger brother's initiative, and this is a very detailed working through of kind of how you adapt a curriculum in the computational age, which I encourage people to look at. I think it's really worked through in detail, kind of what the mechanisms for assessment are and all that kind of thing. I'll show you one more thing in the computational age. See if I can pull it up. I may not be able to. One of the things that's become possible with LLMs is to build tutoring systems that are purely automatic. So we're building one, we're almost finishing building one for a basic algebra course, which is something where a student can sort of on their own interact with the computer and really learn algebra. People have been trying to do this kind of independent, pure computer interacting with students thing for education for 70 years. It's always failed in the past. I think we're finally on a path where it's going to work. And it's a complicated stack of technology. I mean, let me see if I can pull this up. Let me see if I can find it. I think it might not be on this computer easily. Yeah, I think just one. Let me do one try here. This doesn't work. I won't. I'll give up. But I want to. If I can, I'd like to show you this. And really learn algebra. People have been trying to do this kind of independent, pure computer interacting with students thing for education for 70 years. It's always failed in the past. I think we're finally on a path where it's going to work. And it's a complicated stack of technology. I mean, let me see if I can pull this up. Let me see if I can find it. I think it might not be on this computer easily. Yeah, I think might be in luck. One try here. Might be in luck. This doesn't work. I won't. I'll give up. But I want to. If I can, I'd like to show you this. People have been trying to do this kind of independent, pure computer interacting with students thing for education for 70 years. It's always failed. All right. I don't know if this will work. Try it. You got to see some technology that doesn't really exist yet. All right, let's try it. Let me see if I can find it. Is this working? Come on, wake up. Up, here we go. Might be in luck. There we go. Might be in luck. Okay. Let's see. All right. So this is let's take a look at the table of contents. Let's try, I don't know if this will work. Graphing quadratics. Graphing y equals ax squared. Okay, so there's some things that look like kind of traditional textbook, but let's take a look. What happens if I say continue reading? Now, why is this graph steeper than the graph of y equals x squared? Let's see where we go here. I think I'm supposed to type in here. Oh, there we go. Well, let's see. So this is because it has a bigger number in front. Try that, see what it does. Graphing quadratics. Again, this may not work because I think I don't have the latest version of. Okay, so there's some things that look like. Sorry, can't show it to you. Textbook, but let's take a look. But what's really interesting here is that I can really have a conversation with the system, and it kind of keeps track of. It really keeps track of kind of going through this curriculum, and we expect to be able to do this for lots of other courses as well. that's really adapting. That's really taking traditional curricula and being able to help them computationally. I think the much more interesting thing is being able to actually present subjects in a computational way. And in fact, I personally have been, for people have asked me for a long time how best to do that. And I started about a year ago writing kind of a course intended to introduce computational thinking. Actually, that is on the web. The beginnings of that course are available on the web. Just the very beginning. Let me see if I can pull it up and show it to you. Where is it? That's really taking traditional curricula and being able to. So this really, I think, starts from very basics, and I can give you guys a link to this. I don't have very many sections yet. It's still a work in progress, but it perhaps gives a sense of how to present things in terms of computational thinking. It's in the chat. Introduce computational thinking. Actually, that is on the web. It's a good topic, and our company has done a lot with kind of figuring out how to adapt computational thinking ideas, how to present them, how to deploy them in actual settings, both in higher education and in higher education. Our products for 3 decades have been pretty universally used in countries like the US. Basically, all large universities have site licenses for our technology, and it's very widely used in courses by students, et cetera, et cetera, et cetera. I don't know what the story is in Malaysia, but certainly in the US, it's pretty much universally used. The integration of sort of the latest round of computational thinking into courses has happened in some places, but there is vastly more that can be done to really make sort of computational X for all X in actual settings, both in higher education and in higher education. Our products for 3 decades. I see somebody talking about Maple. Maple is just a computer algebra system. It's really a very tiny corner of what we try to do. It's actually got.
Is it still alive?
Not really.
Not really.
I don't think so. I think it's. I kind of feel a little bit of responsibility because it got launched when I launched my first system called SMP. The very event at which I launched that was the place where those folks sort of got the idea of building a system like this. But they really were focused on computer algebra, doing algebraic computation, which is by now probably a few percent of what Wolfram language focuses on. So let's see.
Joshua, when you show the model of ML and neural network incredible, my question is, what would be the fields that involve for quantum machine learning, algorithm, and the platform? QML.
Okay, so well, gosh, a few things to say. First of all, we can talk about quantum computers. I started studying quantum computers around 1981 or 1982. So a long time ago, and didn't think they were going to work. I actually studied them together with a physicist I knew named Richard Feynman, who was fairly famous. We both, I think, concluded that quantum computers wouldn't work. So now many years go by, and a modern version of that issue is still there. See, the issue is in quantum mechanics, one's thinking about sort of many threads of history operate in parallel. That's great. If you're trying to do a computation, you can do many threads of computation in parallel. But then in quantum mechanics, you say, well, then we have to make a measurement. We have to figure out what actually happened in the quantum system. And in the standard formalism of quantum mechanics, it's just this mathematical operation, make a measurement. But in reality, you have to do that measurement. And that measurement takes a certain amount of effort. And what we're doing is there are many threads of computation going on inside the quantum computer. But for us to know what the answer is, we have to knit those threads together to match that with our belief about the world, which is that definite things happen. There's a definite single thread of experience. And so in our models, we start to be able to see what's involved in knitting those threads together. And it turns out that the advantages you get from having those threads run in parallel Probably, we don't know for sure yet. We don't know in all cases. Probably those advantages are more than compensated for by the effort that it takes to knit those threads together. So although the study of quantum computing is very interesting, there's a lot that can be done with the formalism of quantum mechanics, which actually is very similar to the formalism of what we call multi-computation that's come out of our physics project. And it's also very interesting to understand the hardware, the physics of things that can be used for computation. The actual sort of flag that you can wave saying this is a quantum computer, I don't think is going to work out. Although there are things like optical computing, which you can think of as being sort of a little bit like quantum, but they're really not from an underlying physics point of view. Now, when it comes to quantum machine learning, people mean different things by that. There is a possible meaning for it that I think is pretty interesting, which is in something like ChatGPT or an LLM in general, you're basically at every step, you're picking your favorite word to put down next, and you're making a single path of the words you put down to write your essay. But in fact, the LLM has a whole stack of possible words, and you could be following many paths of what to write next. And one of the things that's been the subject of quite a few, there's a bunch of companies we've been involved with, et cetera, that are trying to do this, is to say not just let's write down one word at a time, but let's look at this stack of possible words, let's make this whole graph of possibilities, and let's kind of try to find a path that ends up in a particular place. That's something which has the spirit of quantum mechanics. It's not actual quantum mechanics. It's not running, it's not using quantum mechanics at a physical level. It has sort of the spirit of quantum mechanics as applied to machine learning. And I think there's a bunch of interesting things to do there. And it's not yet clear how to make that practical, but that's a direction that I think is pretty interesting to go. Let's see. I think there's a question here from Diane. I can't say your names, I'm sorry. How about researchers who did research in numerical analysis, algebra, explore or extend their research to AI? How can people who have studied things like numerical analysis and algebra extend to AI? Well, you have to understand something about the foundations of AI. And it's not a lot of progress has been made there. One can, from an engineering point of view, one can see that LLMs work. Why do they work? It's difficult. I've tried to study that a bit. I think some methods from mathematics can allow one to understand things about the structure of meaning space, what the differential geometry of meaning space, but it's pretty difficult. I would say the best way in is probably the things that I've tried to do recently using these very simplified discrete models of machine learning. I think that's a place where you can actually see kind of where you can engage mathematically with what's going on. But I think there's tremendous opportunity, although it's not clear how it's going to work out. Because the question is, are there laws, are there things like natural laws about LLMs? And are there, for example, is there a psychology of LLMs? Is there a way of kind of making overall statements about how an LLM will behave? We don't know yet. These are things that are still out there to be figured out. But I think from a traditional math point of view, I think that, for example, the thing that I wrote recently about the foundations of machine learning is a good place to start, because that's something where you can actually engage with traditional mathematics and what's going on. But I think there's tremendous opportunities. Questions here about scaling laws.
Yeah, scaling laws.
The question is, are there laws, so things like natural laws, the funny thing about scaling laws is it seems like every different person means something a bit different by scaling laws. It's kind of like if you make a bigger neural net, you feed it more training data, it'll get better. That's what it ultimately comes down to. I think what we're seeing in machine learning, we've seen this many times, is there are these thresholds that get passed. So in 2011, the big thing that happened was that image identification by neural nets got solved. And that was a surprise. It was kind of an accident, but it happened. Now, if you look at how has image identification progressed in the last 13 years or so, the answer is not much. It's really just incremental progress. So similarly, things like speech to text, that got solved. It's going to get incrementally better. Different things get solved and then they get incrementally better. The thing that happened with ChatGPT was the ability to produce things like essays. That kind of got solved. It will get incrementally better, but there will not be a dramatic step there. There are other things. The ability to generate videos, that's in the process of getting solved. Not quite there yet, but that will get solved. The ability to do, understand things in robotics with neural nets, that will get solved. But what typically seems to happen is things make this jump. There is a breakthrough. It's very much like what we saw in that biological evolution work, where you have kind of a plateau for a long time, and suddenly there's a breakthrough and things get solved, and then it's kind of incremental progress after that. So I don't think the current, what we see right now with LLMs and so on will get incrementally better. But the real value is in how to harness those LLMs for practical uses. So, for example, our notebook assistant is going to be really useful. It's using LLM technology that has taken a while to kind of wrap things around and tweak it and so on. But it is really LLM technology that was part of the breakthrough from nearly 2 years ago now. But it's what's important there, what's really adding value there is the harness around that LLM technology. And I think that's what we're going to see in most places. The real value, the real sort of progress comes from taking this core technology and building around it. Now, it is the case we're involved with, and in fact, a bunch of people are using ideas of mine to try and get things beyond transformers as ways to do machine learning. And there are a bunch of different ideas, whether it's things to do with hypergraph rewriting, things to do with symbolic computation and so on. It so happens that a bunch of ideas of mine people seem to feel that those are relevant. None of those initiatives has yet worked out in a big way, but there's certainly possibilities. I don't think they will be dramatic. I think they will be important in practical things. For example, one will be able to start running something with the kinds of capabilities that I showed you with Notebook Assistant, or be able to run that on a phone. That's not possible right now. It requires too big a system, too many. A lot of what neural nets do right now, LLMs do, is a complete waste. The fact that a neural net is sort of memorizing the population of Kuala Lumpur in some way, in the 7th digit of some weight somewhere in the neural net, there's some encoding of that, or it's probably distributed across many things. That's not something that should be in the neural net. That's something that the neural net should just ask a tool for that answer. The neural net should contain only kind of the linguistic structure and the kind of common sense information necessary to do computations. And I think that's what we will see, is kind of a slimming down of neural nets to the point where they are just a layer, and underneath is actual computation. The fact that a neural net is sort of memorizing. Let's see, there's a question here about transitioning from computer science to computational X. That's I think, a good question to ask about. So, students, at least in the US, people say, what am I going to study in college? Oh, computers are important in the world. I should study computer science. That's not really what they should be studying. They should be studying computational X. They should be studying how to take the ideas of computation and apply them to every other field. It's knowing how to write a loop and how memory gets allocated and how variables work in the innards of a computer, or how the quicksort algorithm works. It's irrelevant to using computation for 99% of what people should be using computation for. What's needed is to teach computational X, to teach the foundations of computational thinking so that people can apply them in all the different things that they might be doing, whether they're in the mining industry or the banking industry, or whatever else. The things that have been the traditional kind of areas of computer science really aren't relevant. What's relevant is computational thinking, and the thing that in a sense has been my mission is to make that computational thinking accessible by building our computational language so that people can work in terms of images, in terms of graphs, in terms of maps, in those kinds of terms, can do things computationally with the things that are relevant for these different fields. And that's, whereas in computer science, you really are looking at sort of what computers intrinsically do. What one's really interested in computational X is what this computational paradigm makes possible. Now, I have to say that on the theoretical side of computer science, I'm a big enthusiast of theoretical computer science and of practical software engineering, but that's a small fraction of people who should be kind of studying the kind of engineering details of how that works. The vast majority of what needs to be done, where computation can be applied, is really in this computational X area. I mean, to fill that in further, when it comes to programming, the vast majority of programming that's even done today shouldn't be being done. It's simply, even with Wolfram language, many things that people spend huge amounts of effort writing C code, Java code, Python code, whatever for, it's just pointless, because it corresponds to tiny pieces of Wolfram language code that we already automated. And, the thing that has happened is that people who are sort of doing programming for a living, so to speak, are used to this idea that they're giving sort of a specification for what to do, and then they spend a month implementing those things. One thing that's happened a lot with Wolfram language is a lot of the CEOs and CTOs of tech companies themselves use Wolfram language. And they use it, they have a very good workflow, because what they're doing is they think of something they want to do, they find it easy to implement that, they get it implemented. But then they go on and they have another thing they want to implement. Their thought process is a lot about the computational thinking of what do I implement next. Whereas a typical programmer is doing something much more mechanical. They're not thinking about what to implement next. They're simply thinking about the mechanics of the code they have to write. Most of that mechanics can be automated and even has been automated. And it's this kind of anomaly in the world that it's still the case that there are a lot of people sort of doing by hand things that are really completely automatable and automated. And in fact, people sort of realized when ChatGPT came out that it can write big blobs of low-level code that, again, automate some part of this. Even that is really not necessary, because our goal in Wolfram language is to take those big blobs of code and to figure out what are the thousands of blobs of code that one typically needs to use, and just make those functions in our language. That's what we've done, so that you can automate what needs to be done. So that's kind of I think the future is really, how do you apply computational thinking, computational X, to all these different fields? That's what people need to be learning. They can automate the process of actually getting the computation done. What they need to learn about is how to think about things in computational terms. How do you take a problem that you have, a practical problem about, I don't know, if you're some practical problem about forestry and, cutting down, deciding which trees to cut down or whatever else. How do you take a practical problem and turn it into something that is computationally accessible? And that's the thing people should be learning. That is the really high value thing to learn. And in terms of the mechanics, we've gone a long way with Wolfram language. We've gone even further as of today with the notebook assistant and making it possible for people to actually take what they're thinking about and make it computational. And that's, I think, the key thing that really is important to talk about. Maybe one or two more questions here, and then probably.
I think that's about it. You have answered the computational X. The other one is comparison between ChatGPT and Mathematica and syntax codes. And yeah, that's about the main thing there. Is there any difference between Wolfram and Gaussian 09?
We've gone even further as of today. Gaussian 09 is a electronic structure. I think you're talking about the electronic structure program for computational chemistry. We've come a long way in computational chemistry. We will soon have our own electronic structure mechanism. We do not have that yet. We can do a huge amount of stuff in computational chemistry, not electronic structure yet. As a matter of fact, machine learning gives a huge boost in being able to do those kinds of computations, and people have built things using Wolfram language to do that, but we will have our own built-in version of that soon. I think Gaussian
That's about it.
09
Yeah.
is a
I noticed that in
program
moving from Mathematica to Wolfram
we've come a
Notebook
long way in
AI
computational
and
We
all
will
this
soon have our own
irreducibility
electronic
and
structure
computation,
mechanism. We do not have that yet.
you're
We can
quite
do a huge amount of stuff in
close
computational
to
chemistry,
how
not
we
electronic structure
think,
yet. As a matter of fact,
how the
machine
mind
learning
works.
gives a huge boost in being Yes, I mean, that's a whole other topic. But I mean,
Yeah.
one question is, what I think LLMs are a huge kind of window into mind-like activity. And I think one of the questions, which I was talking about a little bit earlier, is there a theory of LLMs? What can you compute? What can you understand about how LLMs work? That's kind of, there's a similar problem for neuroscience. What can one understand about how minds work? We kind of know the details of individual neurons. We know things about kind of the overall level of psychology. Is there an intermediate level of description? Is there an intermediate actual science of neuroscience? It's been hard to find that. I think that we have a chance now through LLMs as an experimental domain that's much more accessible than biological brains. We have that. We also, I think, have a bunch of methods that have come from our physics project for understanding systems that have the kind of complexity that we see in neuroscience. And I'm tentatively hopeful that there may actually be some real science that can be done there, sort of understanding, just like this recent work I was doing, which I did not expect to work on biological evolution. I had tried to study that question back in the 1980s and had not managed to get it to understand how it worked. And finally, earlier this year, I did some experiments that I had actually tried in the 1980s, but now I had a different intuition that came from what I know about machine learning, and I pushed these experiments a bit harder, and they actually worked. And that gives one this whole way of thinking about things. And I am sort of hopeful that there may actually be that it may be possible to make similar progress in areas like neuroscience. We'll see. It's something to look forward to, something to be involved with. I should say for people, there's lots of resources that, well, you can find lots of stuff that I've written. You can find lots of resources from our company. I also will mention our summer schools, there are actually opportunities for educators as well as for researchers at those summer schools. So please do reach out to us if you're interested. And the thing that there's just an exciting moment here in terms of both the technology and the science that exists. And I think it's a great opportunity for people to really sort of grab the future and be able to do exciting things with it. And I think it's something where the playing field is very level. That is, it's not like there's a lot of people in one place who already know all about this. None of us know about it. It's a new, we've just opened up this new area, both in terms of the technology and in terms of the science. There's a new area that's been opened up, and there's a lot of exciting low-hanging fruit to be picked by anybody who has the kind of initiative and energy to do it. So I think I'm just encouraging people to get involved in these things.
Yes.
All right, we should wrap up there.
Yeah, we should wrap up. Thanks, Stephen. That was fantastic presentation. Just before you leave, we would like to take a photograph with everybody present in Zoom. So if just hang on.
Now I get to see you all.
Let's everybody.
Cameras,
Cameras.
That's nice.
Cameras, please.
I should have suggested that at the beginning. I probably would have given a better talk if I'd had that at the beginning, because then I know roughly what. I'm just encouraging people to.
Come on, guys, cameras.
Yes. All right, we should
please. We should everybody switch on your cameras. Thanks, Stephen. That was fantastic presentation. Please, we would like to take switch on your cameras. Everybody present in Zoom. There was Dr. Hashima from NASA earlier. I see our local Wolfram agent, Peter Lim here.
Satu kelas lah.
That's nice.
So untuk maklum,
I should have suggested
We
that at the
can't
beginning.
switch
I
on.
probably would have given a better talk if I
What is this?
I know. We're getting there. We're getting there. More people joining. Let's see.
Shah, there's a complaint that they can't switch on their camera because it was switched off by you. Please
Zoom could do that.
switch on a camera.
Okay, noted, Prof, noted.
Okay, all right. Please switch on OEM's Peter Lim complained that, yeah. Wolfram agent Peter Lim here. All right, thanks guys. Nice to see you all around.
That's nice.
Thanks for joining us.
Thank you.
We can't switch on.
Nice to meet you all.
What is this?
Getting
a mirror
there. Now this is when everybody actually switches their camera off. Right, right when we're wrapping up. But anyway, very nice to talk to you all.
Nice to have you around, Stephen. There was a fantastic talk. I must say I was frozen in time with Mathematica 20 years ago, and this talk really opened my mind to a lot of
Modernize.
stuff. Modernize.
It's
Yeah.
we've done a lot in these
Yeah.
years. It's been
Yeah.
accelerating
Yeah.
actually.
Right.
So anyway, have fun with it. Right. So nice to
All right.
talk to you all.
So
bye.
they will send you an online cert. The secretary will send that to you.
This is
Is it
when
true,
everybody switches their camera off. Right,
Nazri?
when we're wrapping up.
Cert, right? I can't hear you.
Nice to
You're
talk
muted.
Yep,
Okay.
we will send it.
That'll be the cert. Yeah, all right.
Yeah,
Okay,
thanks
thanks,
again.
Stephen. Good night.
Okay.
Have a good
Bye.
have a last. All right, for everybody else, your attendance should be displayed now.
Modernize.